I hope all of you had an exciting day so far. Let me first thank the organizers and the reviewers for their good job. My talk is about recovering information from recorded production data and using it for understanding and optimizing failure. The title is a bit more complex. I hope at the end of this talk you have understood the title and the methodology as well. Now let us consider a real-world production environment. Something like bottles come in, are cleaned, are filled, and then packaged. What we are dealing with are three different objects. First, we consider raw data from such a production environment. Then, after some computation, we get peak correlations for binary time series. And at the end of the day, we recompose the results from the peak correlation analysis to some net graphs. And this is what we're going through now during this talk in two iterational steps. So this is the data object coming from a market leader manufacturing execution system. The advantage of this approach is that we can get lots of real production data from several companies and all of them following the same data model, which I describe shortly. So this is an export of a database. The header is quite huge, more than 100 columns. But what we are interested in is only three data objects, namely the machine ID, the time information, and the status event. So let us have a look at the first event row. So it's a specific machine ID sending that at this time, this status took place and it ended 1 second later. So we have the date, we have the hour given in seconds of a day, and we have the end hour in seconds of a day and the duration time. What is really important is that this, even if it's a number, 105, the status value has no real or rational or natural meaning, but only a categorical meaning. Even more, a semantical meaning. And usually there is for each production company a kind of list where the company associates with all of these numbers a semantic status, such as standard operation, mechanical failure, jam, technical failure, and so on. So we will come back to this point later since it has an impact on our methodology. We now want to understand more or less the structure of this data. So what we can extract from this raw data object, for each machine of that production plan, we get a kind of time series given by the events of status changes. And we used to plot such time series for 1 day. This is sort of standard window size we usually start to have a look at. What we see for this machine is that there is almost a line for the status value 2. This is an important value for this company since 2 means standard operation. So we can also see that there are interruptions, which means that the machine is not operating at the times. On the other hand, you see lots of dots which stand for non-standard operating status values. And there is a weak point of these graphical plots. Namely, if there is a status value which is not standard operating, there must be an interruption of the so-called 2 line. And in fact, there is an interruption, but we cannot see it due to the resolution and the dot size. So usually we have 86,400 of such dots, and 1 or 2 dots or a non-standard operation that takes roughly 1 or 2 or 3 or 4 seconds is not visible in this way of looking at the data. So now let us go our step, which we have done 1 year ago when making this first part of that work. We called it Iteration 1. The idea was to compute from the raw data correlation patterns. I will explain this Iteration 1 step again, which was the subject of a recent paper and not of the actual work. In order to understand the core idea, we compare 3 time series for 3 machines on the same day. And we look at the 2 line, so the status values associated with standard operation. You see all 3 machines most of the time are running regularly. That's good. And we also see that all of them have a frequent non-standard operating status. How can we compare these machines and look if there's a kind of correlation? So first of all, we look on the interruptions again of the 2 line. So the visible interruptions. And what we see is that the visible interruptions here, for example, and here, appear again on the second machine and on the third machine. And they appear almost at the same position. So we can suppose that there might be a correlation of the on-off behavior of that 3 machines. And then we look at the second day, and what we see is we do not find such longer interruptions. And we do not see a similar interruption pattern between the 3 machines. So this might be frustrating and say, okay, so this was a case on the first day. But we see that there are lots of non-standard operating status, probably so short in time that they are not visible. So what we can do here is we zoom in on day 2 on a 30-minute window rather than 24 hours. And in fact, we will find interruptions. And we find interruptions that seem to be in some sense correlated. So here we have an interruption in all 3 2 lines. So let me explain for a moment. This is not only zoomed in, it's also only concentrated on the 2 lines of the 3 machines. So blue is that line, orange is that line, and green is that line. And zoomed in a 30 minutes window from 9 o'clock to 9:30 in the morning. So it's around here somewhere. And we see these interruptions which may correlate with each other. So here, 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 and here. But we also see 2 other interesting features, which is there is an individual interruption here, and we see that the width of this interruption is not identical. So what we might suppose at this point is that there is a correlation, but it's overlapped with some kind of stochastical noise. Now let me speak about the core computation. We wanted to compare the raw data, the time series for each machine with each other, and we want to look for correlation. So there is the standard choice of cross-correlation analysis. In order to apply a cross-correlation analysis in the standard way, you need metrical data. You have to calculate a computer mean value, you have to normalize by means of a metric, and this is not possible since I remember that our time series are of categorical type. So the number 105 or the number 2 has no real meaning. So what we have done in order to apply cross-correlation, we have binary coded the categorical time series. And this is the reason why we called this first step Iteration 1. What we have done is we have set the status value, which is associated with the standard operation, to be the category 0, and all other status values, which are non-standard operation, the binary category 1. After coding the categorical time series in this way, we can apply cross-correlation computation, since there is a meaning for mean value and normalization. And what comes out is a typical cross-correlation picture by applying the cross-correlation computation for different shifts. So this, for example, is the result of the cross-correlation of the binary time series, shifted from minus 300 to plus 300 seconds between the machines 4 and the machine 6. And the meaning of such a result is that for the shift of around 50 seconds, there is a strong maximum, which means at this position, the two binary time series are most equal, overlap in a most similar way. And we see that if we do not shift 50 seconds, but 45 or 30 seconds, this similarity decreases in a strong way. So we call this a sharp peak, and we assume that this peak is a measure of correlation, of statistical correlation. So for these three machines, we find three strong peak distributions with different time lags, so around 50 seconds, around minus 30 seconds, and around plus 20 seconds. By the way, in the first paper, we have shown that in many cases there is also a kind of addition rule of cyclically pairwise correlating machines and addition rule for the time lags. So this is an interesting feature for the expert at the end of the day in order to make a kind of plausibility checks with the peak correlation analysis. So our last subject in iteration 1, which then will be repeated in iteration 2, is a representation method. So now we take all peak correlation results and we filter them. So if we compute the cross correlation for all binary series, we will find many results that do not provide us a strong peak. So this might mean that the machine is completely on or completely off, or the status of the machine does not depend on the material flow, like an oven that is heating something, even if there is nothing inside. So there might be many reasons why some machines do not contribute to the peak correlation patterns. But all the machines that contribute can be extracted from the graphical or from the cross correlation results by means of simple characteristic parameters, which is the time lag. And we have introduced a kind of peak score that measures the sharpness of the peak. And at the end of the day, we produce such net graphs. So this net graph is the peak correlation pattern of a complete raw data object coming from a production plan on one day. So the green bubble is a machine where all time arrows end. The red bubbles are machines where all time arrows start. And the yellow bubbles machines where time arrows can start and end. So somehow they are in the middle. The numbers that are written here are the time lags between these pairwise correlated machines. So these are the three objects: raw data, peak correlations, and net graphs on iteration 1. And now an expert could use these net graphs in order to validate the daily dynamics of the production by looking at the time lags, at the logical position of all the machines within these nets. You can also do kind of plausibility check by these addition rules, which I have explained before. Now let us come to the results of our actual work. It's iteration 2. We have repeated the complete computation in a specific way in order to extract from the raw data objects more specific information about the correlations between the machines. So let me recall this graph that we had before with the interruptions of the zero line. The basic idea now was in iteration 2, not only look at the trivial binary coding, which was 0, standard operation, 1, the rest. Now we look at one specific non-standard operation status, and this is the category 1 now, and all other status, the complement, is associated with the standard operation status as category 0. So we create a new binary series which focuses on one specific non-standard operating status value. And obviously there is a heuristic depending on the number of non-standard operation status values, and we have to compute all these binary coded possibilities. We do this can be simply automated, and what we find is very interesting. If we look at two of the three machines that I have shown before, we find a kind of split, a kind of degeneration of the cross-correlation results. So for 2 machines, this is only for 2 machines, we find 4 different peaks. We find much more cross-correlation combinations that do not lead a sharp peak. But we find such peaks not between the machines, but between the machines with specific non-standard operation status, such as a failure. And if we plot this in a net graph type, for all the machines of a production plant, we now find many bubbles with many time arrows, and each bubble is not a machine, but a specific non-standard operation status of a machine. Let us, at the end of this talk, extract 2 pictures which give a result in iteration 1 and 2. So this is 2 machines which in iteration 1 turned out to be correlated strongly with a time shift of 42 seconds. If we look at the same representation in iteration 2, we see a split and we see a correlation between the state of machine 3, 107, so red means machine 3 changes its status before, and the status which appear to be correlated is 107, which is a side stream jam. And there are 3 different correlated status of machine 1. Namely, machine status 105, which is a sync jam, status 107, which is again a side stream jam, and a status 111, which is an intrinsic disturbance. And now the interesting aspect that these 3 types of malfunction have different reaction times, have different time shifts. So the first time shift is 39 seconds, the other is 53, and the third 52 seconds of time shift. So we can conclude that probably the time lag in iteration 1, 42 seconds, is a weighted mean of these 3 possibilities, and probably the weights of these mean computation depend on the frequency of these correlations. So what we have here is a hypothesis for a kind of failure propagation between 2 machines. So this is the end of my talk. I hope I have explained the methodology as well as the automation potentials, and thank you for your attention.